Okay, in this example, we're going to simplify the expression the square root of the fraction 6 over 15. Now, I know there are different approaches that you can do with here. In some ways, sometimes you can make it shorter by doing one approach over another. I'm just going to go through a general strategy for this example. I do know that there is a way that you could do it that might feel a little bit quicker. But as I said, I'm just going to look at a general approach to doing these problems. Now, since the radical sign is over the whole fraction, I'm going to go ahead and split it apart into the square root of 6 over the square root of 15. Now, this radical on the bottom is not a perfect square. When you are simplifying radical expressions with fractions, one of the goals is to get rid of all radicals from the bottom of the fraction. Since 15 is not a perfect square, we have to go through a process called rationalizing the denominator. Now, if there is only one term in the bottom, we just have to complete the square. So since we have a square root of 15 in the bottom, we will multiply the bottom by square root of 15, which is going to overall give us square root of 15 times square root of 15, which is the square root of, I'm going to double check, 225. I thought so. It's getting late. I'm getting tired. So we got the square root of 225 there. Now, we can't just change the bottom because we need it to be this way. We have to do things to balance it out. So if we multiply the bottom by the square root of 15, we also have to multiply the top by the square root of 15. This means essentially what we're doing is we're multiplying by 1, and if you know anything about math, after like elementary school, multiplying by 1 doesn't actually change the value of the expression. 5 times 1 is still 5. So multiplying by 1 isn't changing the value, but it will change what it might look like here. So now that we got that out of the way, we're going to multiply the top here. Radical 6 times the square root of 15. So 6 times 15 gives me 90. So we have the square root of 90. Now we just have to go through and break down the radicals. Let's see. The square root of 225, well, 225 should be a perfect square. It's 15 times 15. I know it's a perfect square because we created it that way. So the square root of 225 is 15. Now for the top, the square root of 90, well, 90 isn't a perfect square, so I want to ask myself, is there a perfect square that goes into 90? The answer to that is yes. 9 goes into 90. 90 is 9 times 10. The square root of 9 is 3, so this simplifies into 3 radical 10. In some cases, we may need to check to see if we can reduce. So in this case, if we look at the top coefficient here, and the bottom number, is there anything that goes into both 3 and 15? Yes, there is. 3 goes into both of them. So we'll divide them both by 3, giving us 1 radical 10 over 5, or just radical 10 over 5. Now, some students might ask, why don't we divide both the top and bottom by 5? Because 5 goes into both 5 and 10. But on top, that's not a factor of 5 that we're seeing. It's not a factor of 5 that we see here. It's a factor of the square root of 5, which is not the same as a factor of 5. So we can't divide it because one's underneath the square root while the other isn't. Now, as I said, though, there are other approaches. Like at the beginning, in some cases, I could have actually reduced that fraction in the first place. I could have reduced that fraction to, 3 goes into both, so I could have reduced it to 2 over 5, and then simplified it with the same exact process from there. Sometimes you can reduce beforehand, sometimes you can't, sometimes, there's different situations that can come about. But here is a general process to going through these problems. And the more comfortable with them that you are, the more different approaches you can take. Now in this example, we're asked what is the cube root of 2n over 9m? in reduced radical form. So again, the purpose of simplifying radicals is to get rid of the radicals in the bottom of the fraction. So when we handle this, we're going to go ahead and start by separating it into the cube root of 2n over the cube root of 9m. And there are different approaches that I could take here. But I'm going to just start with a very basic approach, and then I'll just emphasize another approach I could have taken at the end of the problem. So now the goal here is to complete the radical. Currently, this is just 9m to the first power. We need a perfect cube to be in the bottom. So for a perfect cubed, we would need this expression to occur 3 times, multiplied by itself 3 times. In other words, we want to multiply the bottom of this expression by the cube root of 9m squared. Because currently over here there is 1, and then when you multiply them, you would add the exponents, making it the cube root of 9m to the third. So this is one approach we can take for these problems. But of course, just like the first problem, we have to balance it out. We can't just multiply it or change the bottom all willy-nilly like. So we're going to also have to multiply the top by the cube root of 9m squared. If we do this, that's going to give us, not as pretty, but it's going to give us the cube root of 2n times 9m squared, in parentheses, squared. Now on the bottom, it should be a perfect cube. The radical and the index are going to cancel out, giving us just 9m. On top, however, it's going to be a little bit more complicated. I'm going to have to deal with this first before I can do anything else. So it's going to be the cube root of 2n times, when you have a product inside parentheses raised to a power, you can give the exponent to each one individually. So 81m to the second, which we can then multiply and get the cube root of 2 times 81, which is 162 nm squared over 9m. Afterwards, you need to try to break down the radical. The n and the m can't be simplified because, well, there's not enough of them to be a perfect cube. However, 162, there is a perfect cube that goes into 162. 27 goes into 162. It's 27 times 6. So the cube root of 27 is 3 cube roots of 6nm squared over 9m. And then we can simplify this further. 3 goes into both 9 and 3, reducing it to 1 cube roots, or just the cube root, of 6nm squared over 3m. And that would be the final simplified version. Keep in mind we have been assuming non-zero denominators. I could have taken different approaches as well. I could have multiplied right here. I could have changed that to 81 over m squared in the first place and actually multiplied it. I could have also rewritten it at the start as the cube root of 2n over the cube root of 3 squared, because that's what 9 is, times n. And then I would have just had to multiply by the cube root of 3m squared. So there's a number of approaches sometimes you can take for these problems, but what I gave you at the beginning was a general format that I could do. Now in this example, we are simplifying the expression 1 over 2 plus the square root of 5. Now with this expression, again, the goal is to get rid of the radical in the bottom. And if I just try to multiply by the radical like I've been doing, this is what happens. This is not correct. I'm just showing you what would happen. So as I've been doing, I would try to multiply by the radical. On top, that would give me just radical 5, or 1 radical 5 if you prefer. And on the bottom, I would distribute it to both terms, having 2 radical 5 plus the square root of 5 times 5, which is 25. This is indeed a perfect square. However, we would still be left with a radical on the bottom, and it wouldn't solve the problem in the long run. So how do you handle it when there's 2 radicals on the bottom? Or 2 terms, on the bottom of the fraction? Well, that's where the conjugate comes into play. And we actually used it in an earlier lesson this year. 1 over 2 plus I. Getting rid of the i's in the bottom, we use the complex conjugate. Well, we're going to use the conjugate here to get rid of the radical in the bottom of the fraction. So the conjugate, if you recall, is the same expression, just changing that sign in the middle. So we'll multiply the top by 2 minus radical 5 over 2 minus radical 5. Multiply top and bottom by the conjugate of the bottom. We would distribute things out. 1 times 2 is 2. 1 times negative radical 5 is negative radical 5. On the bottom, they are conjugates, so you could take the shortcut. I'm going to write out all the distribution just because I believe it's kind of important that you know where the conjugate comes from. But 2 times 2 is 4. 2 times negative radical 5 is negative 2 radical 5. Radical 5 times 2 is positive 2 radical 5. And then positive radical 5 times negative radical 5 is negative radical 25. Now, because they are conjugates, these middle 2 terms should cancel out. So in the long run, for conjugates, all you really need to multiply is the first times the first and the last times the last, because the middle terms cancel out. But that's not the case if they are not conjugates. So if you're going to just mix them up, it might be better to distribute the whole thing like this instead of trying to use the property for conjugates. But that's a story for a different time. Going through to finish this problem, we would try to simplify the radicals. The top one, square root of 5, I can't simplify. However, on bottom, the square root of 25 is 5. So this bottom piece, the bottom piece will become our 4 minus our square root of 25, which is 5. And 4 minus 5 is negative 1. So we have 2 minus radical 5 over negative 1. Depending on the situation, this may be it. Sometimes you might be able to reduce. Sometimes you might be able to split it up into 2 fractions. Typically, you won't see a negative in the bottom. So if you are to reduce, you're going to divide the number on the bottom, the number here, and the coefficient with the radical all by the same thing. So because this is negative, if it was a multiple choice question, they probably would have divided all 3 of those numbers by negative 1. So the number on the bottom of the fraction was positive. So 2 divided by negative 1 would be negative 2. Negative radical 5 divided by negative 1 is positive radical 5. And then negative 1 divided by negative 1 is 1. So most likely, if it was a multiple choice question or an answer bank key, it would probably be negative 2 plus radical 5 as the final answer.